This is the start of a new chapter, work, energy, and power. So we have learned about force. Now we will see that force can do work. In physics, the concept of work is very different from what we know from our colloquial language. The concept of work is very different. It can be positive, negative, or zero, and work is done by a force. Work is done by a force. So therefore, it will be done by a body on another body. So what is the result? What is the effect on the two bodies because of one body doing work on another? And then we will see work done by a constant force or by a variable force, and in particular, work done by gravity, which is a constant force. And the interesting thing that we will discover is that the work done by gravity only depends on the vertical displacement up or down. It doesn't depend on the path taken. And then we will see the concept of energy. Welcome to the portals of real learning. Enjoy your learning. We now start the chapter of work, power, and energy. It's a wonderful concept about work and energy, and it is applicable in so many different situations. We will learn tools which are so exciting, it makes our tasks so simple, and you'll see that as we go along. We are going to talk about the concept of work and an important theorem called work energy theorem, kinetic and potential energy, law of conservation of mechanical energy, and we'll do problems. Let's begin. Work. In our day-to-day conversations, we might say, my mobile is not working, or this idea will work very well. I don't feel like working today. That's all English. In physics, work has got a very specific meaning. Work is said to have been done if there is a displacement of a body or of a system under the influence of one or more forces. What it means is that work is done by a force. And there should be a displacement as well, otherwise, no work. There should be a force and there should be a displacement. Work is done by a force. The interesting thing is, even if there's a displacement, non-zero displacement, the work can still be zero by that force. And it can be positive or negative. Let us see some examples. If you push a wall, you do zero work. Although you are exerting a force, there is no displacement of the wall, zero work. If you push a wheelbarrow, then yes, you are causing a displacement. Let me write that as S, and it's a vector quantity, so there's a displacement. And the force by you is also in the same direction. Then you are doing work, and that work is positive. In a tug of war, the man on the left is being beaten by three men on the right, obviously. The man is pulling the rope and he's exerting a force like that. But because the other three are stronger, he gets displaced like this. The force and displacement are in opposite directions, and in this case, the work done is negative. If a porter is carrying a heavy box without any acceleration and he takes it to some other place, the work done is zero here. The force exerted by this porter on the box is like this, that is a force, and the displacement is like this. The force and displacement are at right angles. The work done is zero. In this case, it is zero. But if there was an acceleration, then that's a different scenario. So now you can guess work done is positive, negative, or zero depending on just one thing. That is, what is the angle between the force and displacement. If the force and displacement are parallel, then the work done is positive. If the force and displacement are anti-parallel, then the work done is negative. If the force and the displacement are at right angles, then the work done is zero. For any other angle, we need to arrive at an expression for the work done. Let us see this example. A constant force in magnitude and direction is applied on this block, as a result of which the block moves up and the displacement is this vector. As you know, displacement is a vector, a line joining the initial point to the final point, and along that direction, initial to final, that is a displacement. There is a force, there is a non-zero displacement. So what is the work done? You might have seen this expression earlier. Work is equal to force into distance, but not any distance. A distance which is in the direction of the force. Here, the displacement is not along the force. The force is to the left, and the displacement is in some other direction. So, if we apply this expression, which is correct, but we want to arrive at a more rigorous expression and also something that would apply in all situations. Anyway, let me take this expression. The displacement along the force is only this much. Let us call it x. The height of this plane is h, and this length from here to here is L, and this angle is theta. The work done is Fx, force into the distance traveled along the force. But what is x? I can write cos theta as x by L. Therefore, x is equal to L cos theta. Work is FL cos theta. Now we know what this L is. When I write F and L, both are vectors without the arrow, it means I'm only talking about the magnitude. So magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between the two vectors. This is the angle between the two vectors. And that is called the dot product of vectors, F dot S. And it is magnitude of F into the magnitude of S. Magnitude of S means magnitude of displacement into the cos of the angle between them. And that is a dot product. That is the expression for work done. F dot S. Clearly, if F and S are parallel to each other, then what is theta? 0. What is cos 0? 1. Then the work done is plus Fs. If the force and displacement are opposite, what is a theta? 180 degrees. What is cos 180 degrees? Minus 1. Work done is minus Fs. If the force and displacement are perpendicular, theta is 90, cos 90 is 0, work done is 0. So the work done will be positive, negative, or 0 depending on the angle between the two vectors. As simple as that. So there may be multiple forces acting on a body, and there's a displacement in one direction. We can calculate separately the work done by each force, and then we can add them all together to arrive at the work done by all the forces summed up. And that concept will be very interesting, very important as we go forward. Work is a scalar quantity, and the unit is called joules. It is actually force into distance, so it is Newton into meter, and we give it a name joules. And in any case, when you do a dot product of two vectors, the output is a scalar quantity. It is not a vector quantity. But it can be positive or negative. That's a separate thing. It doesn't have a direction. Take another look at the same expression. We had work is equal to F into L cos theta. L cos theta was X. And L cos theta is the component of the displacement which is along the force. This L cos theta is that component of displacement which is along the force. Alternately, we can write work as L into F cos theta. What is F cos theta? F cos theta is the component of the force along the displacement. F is this, and theta is this. The component of the force along the displacement is F cos theta. So we can write work is force multiplied by the component of displacement along the force, which is the same thing that we have seen earlier. Work is force into distance along the force. So this expression is just the same thing, that is force multiplied by the component of displacement along the force. And this expression is displacement multiplied by the component of force along the displacement. We can write it both ways. Force into displacement along the force, or displacement into force which is along the displacement. In any case, just do F dot S in each case and you will have the answer. Let's take three cases, very interesting. Case 1, force and displacement are parallel. Then theta is 0, so cos 0 is 1 and work done is positive. Like this case, a mass falls down by a height h. So this is the displacement vector. Join the initial point to the final point. And it falls due to gravity, and the weight, as we know, is mg. Mg is downwards, displacement is also downwards. Work done is force multiplied by the displacement. As simple as that. mgh, and that is positive. Suppose a boy lifts a mass from the ground and puts it on his head, and his height is h. What is the work done by the boy? We are not talking of the work done by gravity. We are talking about the work done by the boy. In lifting this weight, he has to exert a force like this, which is definitely greater than the weight. Otherwise, he can't lift it up. And suppose he lifts it up very slowly, then this force is just a little bit more than the weight. Therefore, the work done by the boy is again plus mgh. His force was upwards. Remember, he is exerting a force upwards to lift the mass, and the displacement is also upwards. They are parallel. Work done is plus mgh. Case 2. Force and displacement are perpendicular. Like the Porter example I talked about, that is 0. Also, if a stone is tied to the string and it is going around in a circle, we know about the centripetal force, which is directed towards the center. What is the work done by this force? At every instant, the force is perpendicular to the displacement. In a very short time, the stone goes from here to here, nearly a straight line, and the displacement is perpendicular to the force. This force does no work. Work is equal to 0 if the displacement is 0 or the theta is 90 degrees. No matter what the force may be whatever. If the theta is 90 degrees or if there is no displacement, then the work done is 0. Third, force and displacement are anti-parallel. Like a body is going with some speed, in a given time there is a certain displacement s, but friction is opposing it. What is the work done by friction? Negative, because force and displacement are 180 degrees apart. If you consider a mass that is being raised by a height h, then the displacement is s or h, but it is upwards. And if I ask what is the work done by gravity, gravity force is downwards, right? Work done by gravity when a body goes up is negative because force is downwards and displacement is upwards. Whereas if a body falls under gravity, then the force is downwards, displacement is also downwards. The work done is positive. Clear? Let's do a small question from NCERT. Work done on a body A by a body B and vice versa. A cyclist is going with some speed and he presses a brake, comes to a skidding halt in 10 meters. During this process, the force on the cycle due to the road is 200 newtons, which is friction. Obviously, it is opposed to the motion. How much work is done by the road on the cycle and by the cycle on the road? When we ask this question, what we are basically saying, work by the road on the cycle means what is the work done by that force which the road is exerting on the cycle. Similarly, when we ask what is the work done by the cycle on the road, then we are asking what is the work done by that force which the cycle is exerting on the road. A part is friction is the force by the road which is opposing the motion. The value is 200 newtons. The displacement is 10 meters. Now force and displacement are opposite. Work done is negative force into displacement minus 2000 joules. Second case, what is the work done by the cycle on the road? The cycle definitely exerts a force of 200 newtons on the road by Newton's third law. But the road has no displacement. S is zero. There is a force by the cycle on the road, but the work done is zero because there is no displacement at all. Now, work done by a variable force. Force need not be constant. So suppose the force varies with displacement in some form like this. Now we can't do F dot S. We can't do F dot S directly. The question is which F would you consider? Force is not constant. If it were constant, then this is perfect. This is not constant. That means we need to take a small displacement, let us say from here to here, a small displacement so small that the force can be treated to be constant during that small displacement. Then the work done is simply this force multiplied by this tiny displacement, a tiny displacement called ds. And this is the value of the force. Then the work done, let's call that dw, a small amount of work done. That dw is f dot ds. We are assuming that the ds is so small that the force is constant. Now, in the next small ds, what is the work done? In the next small ds, what is the work done? If you add up all these tiny strips, then you get the entire work done over the displacement from S1 to S2 positions, which is nothing but the area under the curve. And that in mathematics is called integration. You have dw as f dot s. Work is integration. Integration is an elongated s, which is summation is for discrete numbers. This kind of a curve is for continuous kind of a quantity. Integral of dw is f dot s from some initial position to a final position, and there are integration formulas for us to calculate. We are not getting into integration, but we are definitely going to use a concept that integration is area under the curve. Suppose I have a simple case of force versus displacement. Then what is the work done when the body goes from this position to this position? Just find out the area. This area will be positive because force is positive, and this area will be negative because force is negative. Basically, force above the x-axis, rather, the area above the x-axis is positive, and area below the x-axis is negative. And this concept we should be able to apply. Work done by a variable force. A woman is pushing a trunk on a rough railway platform. She is applying a force of 100 newtons over a distance of 10 meters, and thereafter she gets tired and reduces her force, not suddenly, but slowly or linearly from 100 to 50. And she covers a total distance of 20 meters. Plot the force applied by her. And also plot the frictional force, whose value is 50 newtons, and then calculate the work done by the two forces. Force by the woman. We are plotting force versus displacement. Force in Newton, displacement in meters. She starts with 100 newtons and it is constant up to 10 meters, and for the next 10 meters she covers a total distance of 20. In the next 10 meters she reduces her force applied linearly to 50 newtons. So that is the plot of the woman's force. Friction would be opposing it. So force by the woman, if it is this way, then the force by the friction will be opposite. If I take that as a positive force, it's a vector, right? So I need to give a sign, then this will be a negative force. So minus 50 newtons, and friction is simply constant. That's a part. What is the work done by the woman? Area under the curve. This area plus this area. And both areas are positive. What is the work done by friction? Only this area, which is a negative area. That means friction is doing a negative work. Obviously, friction will do a negative work because friction is opposing the motion of the box, which is going this way. Now, area A1, rectangle 10 into 100. Then area A2 is a trapezium. Trapezium area is half sum of parallel sides multiplied by the distance between them. This side is 100, this side is 50, and this distance between the two parallel sides is n. Half sum of parallel sides into the distance between them, we get 1750 joules positive. Work done by friction is simply this area, which is what? 50 into 20 negative minus 1000 joules. If you have the force displacement graph, you can calculate the work done very easily by simply calculating the area under the graph. This is not force versus time. This is force versus displacement. Work done by gravity, if you consider, it's a constant force mg. The key point, as we'll see, is that only the vertical displacement matters when you are talking about the work done by gravity. First case, simple case, a mass drops by a height h. As you know, the force mg acts downwards, the displacement is downwards, work done is plus mgh. Suppose this body is thrown up with some speed and then it falls down. The work done is still the same because it is F dot S, and S is not distance. S is displacement. Displacement is a vector, distance is a scalar. Displacement is a line joining the initial point to the final point. Doesn't care about how you reach there. Doesn't care about the path taken. So it is the same displacement. Therefore, same work. Third case is a little bit different. A ball rolls down an inclined plane. The displacement is not vertical. The displacement is this. But when you do F dot S, F is mg downwards and S is this L vector like this. Then when you do mg into L cos theta, mg dot L, right? And dot L means L cos theta. L cos theta is nothing but H. So what do you conclude? The body may go whichever way under gravity, but the work done by gravity only cares about the vertical displacement. If the vertical displacement is downwards, then the work done by gravity is positive. If the vertical displacement is upwards, the work done by gravity is negative. See this case, a boy walks up a staircase covering a height h, vertical height h. Work done by gravity, the body is going up. Okay, it is going by some slanting path. That doesn't matter. Only the vertical displacement matters when we are talking about the work done by gravity. And when you go up, the force by gravity is down, so work done by gravity is minus mgh. But the work done by the boy is plus mgh. His own mass is m, so in order to raise himself, he must exert a force through his legs, at least equal to his weight. It should be a little bit more than the weight. So the work done by the boy is at least plus mgh. Clear? What are the units of work? Joule. 1 joule is 1 Newton into 1 meter. 1 joule of work is said to be done when a force of 1 Newton displaces a body by 1 meter, but must be in its direction, right? That is the definition of joule. 1 kilojoule, kilo means thousand, so kilojoules means 10 to the power 3 joules. 1 megajoule, mega means million, so 10 to the power 6 joules. 1 gigajoules is 10 to the power 9 joules, that is SI. In NKS, unit of force is mass into acceleration, right? That is MA. But for work, we are talking of force multiplied by distance. If you multiply this by distance along the force, of course, then it is kg. This will be meters actually. This will be kg meter square per second square. This S is not displacement, it is seconds. In CGS, force is dyne and distance unit is centimeter. So 1 dyne into 1 centimeter is the unit for work, and that is called erg. 1 erg is equal to 1 dyne centimeter. 1 erg of work is said to be done when a force of 1 dyne displaces a body by 1 centimeter in its own direction. We can always relate joules to erg. 1 joule is 1 Newton into 1 meter. We have earlier seen that 1 Newton is 10 to the power 5 dyne and 1 meter is 10 square centimeters. So 1 joule is 10 to the power 7 ergs. Now, that was work. What about energy now? Energy is the ability to do work. A body which is capable to do work is said to possess energy, or energy is the ability or capacity to do work. Now, you may have a lot of energy, but you may not do the work. You may be very lazy, but you still possess the ability to do work. That means you possess the ability to exert a force. Work is only done by a force. If you have energy, if a body has energy, it has got the capability to exert a force. How do we measure energy? Since energy is the capacity to do work, we will say that the unit of energy is the same as unit of work, that is joules. So amount of energy is the work that a body can do. It is the ability to do the work. If a body does work, okay, suppose a body actually performs work, like you take a heavy box from the ground and put it on the shelf, take another one and put it on the shelf, you are going to get tired because you are expending your energy. If a body does positive work, it will lose the energy. Now, that body is doing a work on somebody. Like if you lift a box from the ground, you are doing positive work on that body. So you lose the energy equal to the amount of work that you did. You lose that much energy. Now, work is done on that body. If you lost energy, then he is gaining exactly that much energy. Energy, there's a very big law about it, which is the conservation of energy. Energy can neither be created nor destroyed. It can only transform from one form to another form. So if you are doing positive work on a box, you lose energy and the box gains exactly the same amount of energy in some form. Those forms we will see later. So the interesting thing is this: there is a transfer of energy when work is done. Somebody loses, somebody gains. The units of energy is joule. There are bigger units of energy also in use only for convenience purposes, like watt hour and kilowatt hour. We are going to learn about watts and kilowatts in the next session, which is about power really. But just let me quickly say that watt is power, and let me write power, not W. power is the energy per second or work per second. And this is called watts. So 1 watt is 1 joule per second. That means watt into second is joules, power into time is energy. So if I write 1 watt hour, that is power into some unit of time. It is not seconds, it is hour, all right, but it is still energy. 1 watt into 1 hour. 1 watt is 1 joule per second, and 1 hour is 3600 seconds. So 1 watt hour is 3600 joules. Kilowatt hour is simply 1000 watt hours. So multiply this by 1000, you get 3.6, not kilojoules. This is 3.6 kilojoules. This will be 3.6 kilojoules into 10 to the power 3. 1 kilowatt hour is a work done by a source of 1 kilowatt in 1 hour. Now, talking of heat energy was traditionally measured in calories, not joules, where 1 calorie is about 4.2 joules. Heat was not even recognized as a form of energy. It was just seen as something that needs to be supplied to a body to raise its degree of hotness or temperature. Later on, we realized that heat is also a form of energy. 1 calorie was defined as the heat required to raise the temperature of 1 gram of water by 1 degree Celsius from 14.5 degree to 15.5 degrees centigrade. That is also another interesting aspect. You could raise the temperature of water from 20 to 21 or 25 to 26 or 40 to 41. You need just 1 degree rise. Why are you bothered about from where you are starting? Well, all these experiments are being conducted in an average room temperature of 15 degrees centigrade. So they chose that as a midpoint and 14.5 to 15.5. There's nothing special about this 14.5 and 15.5. Another unit of energy is in atomic and nuclear physics called electron volt. When you look at atomic particles, their energy is small and joule can become inconvenient, though that is a SI unit, so we use electron volt. What is an electron volt? Electron volt is the energy gained by an electron when it is accelerated through a voltage difference or potential difference of 1 volt. And it is called electron volt. 1 electron volt is 1.6 into 10 to the power minus 19 joules. So that was the introduction to work and energy. In the next session, we will talk about power and some other very interesting things about work, energy, and power.